Morning, friends. Yeah, I'm here to take you through random samples and sampling distribution as part of statistical inference, our third topic. I briefly introduced probability distribution because I know we are doing probability theory one or two. Yeah, so if you're doing one, you will have to do probability two. If you're doing two, it means you've already done one. So I found it unnecessary to go through the same basics of probability, when you've already done two questions on probability. So I just gave you a simple introduction, a PowerPoint, simple video, just to refresh your mind. Okay, so today we are going to look at random samples and sampling distribution, for which I know they're also not too new to us. They're not too new to us. Okay, let me start by looking at population and sampling. And we're saying population is a complete set of individual cases objects with some common observable characteristics. Okay, it's a complete set of elements which have something in common. Okay, a part of which is what we call a sample. A sample is just a part of a population. Okay. Okay, here we're saying a particular population has some characteristics that differentiate it from other populations. For example, all four-bedroom residential houses in Kampala, or secondary school children, etc. Okay, but when you look at all those secondary school children, they have something in common. Of course, what they have in common is different from what the four-bedroom residential houses have in common. So if you have several populations, they will be having their characteristics are different from that of the other population. And we are saying a subset of a particular population is a sample. Okay. Okay, so after you've identified the target and that population you can access, the next thing will be for you to select a sample from the accessible population. Yeah, because of several reasons like time, finances, etc. At times you find yourself in a situation whereby you can't study the entire population, but rather you can pick part of the population, study it, and then draw conclusion on the entire population. Okay, that is selecting a sample. You choose part of the population, and after studying that, you can now draw conclusions, or you can conclude about the entire population. We apply this a lot even in our real life. I often use the example of those who cook. If you've made your pilau and you want to know if it's ready or if you put enough salt, you just sample out part of it, and after you draw conclusion, basing on what you found out from that little part of rice you tested. So the same applies with our sampling. We're saying a sample must be large enough to represent the silent characteristics of the accessible population. So the bigger the better for a sample. Because a bigger sample is more closer to the population, and thus it's more, or it's likely to give you more accurate results or information. So we always prefer a larger sample. But still there are some formulas in place which can determine for you the most appropriate sample size. That's in case you've decided to choose a sample. So here we're trying to define sampling as that statistical practice concerned with the selection of a subset of individual observation within a population. I've talked about this earlier. You pick part of the population to represent the population. Okay, now our random sampling. Random, like I said earlier, we've done probability. We've been introduced to probability, and at least we know the things of chance, etc. So random sampling, we've said sampling is selecting part of a whole, part of the population to represent a population. So you're saying random sampling. Random sampling is a method or a technique of sampling whereby all elements in a population are given a chance to be selected. This chance may not always be an equal chance for all the random sampling techniques, but every element is given a chance to be selected. We are going to look at these. We are going to look at the various techniques or methods which fall under random sampling. Yeah, we'll briefly run through them. What makes up random sampling? What are the different techniques under random sampling? Those techniques under which every element has a chance to be selected. Okay. Yeah, here I have my figure there, diagram. You can see on your left, yeah, it's on your left. We have the random sampling techniques. On the other side, we have those which are non-random. Okay, so here we have simple random, cluster sampling, systematic sampling, stratified random sampling. On the other side, we have convenience, judgmental, snowballing, and quarter sampling. I will just briefly talk about few of the random sampling techniques. The first one being simple random sampling. At least this is the most used. Simple random sampling, whereby every element under simple random sampling has an equal chance to be selected. Every element has an equal chance to be selected. Okay, so it means if you're 100 and we need to sample out 80, each of you has an equal chance to be selected. We shouldn't confuse random sampling and simple random sampling. Yeah, simple random sampling is just a part of random sampling. Okay, because there are some random sampling techniques for which every element is not given the same chance to be selected. It's only in simple random sampling that every element is given an equal chance to be selected. Yeah, I repeat. I repeat. I'm saying let's not confuse simple random sampling with random sampling. And I'm saying random sampling is a subset. Rather, simple random sampling is a subset of random sampling. Okay, and I was saying that not every random sampling technique gives all elements an equal chance to be selected. It's only simple random sampling which gives every element an equal chance to be selected. So we'll see these other random sampling techniques like cluster, systematic, stratified. Okay, they don't necessarily give every person an equal chance to be selected. Okay, and how do we do simple random sampling? You can list your elements, write them down, maybe piece of papers, and fold them, put in a basket, shuffle, and then you select the elements. Every element will be having its unequal chance to be selected. So at times in our population, we have groupings, and each of those groups has elements which have something in common. So it's always good to have each group represented in our sample. So under such circumstances, we can use stratified random sampling. Yeah, we know we have groupings, we have groups within a population, and we want each of those groups to be represented. Okay, so what we do under stratified random sampling, we make sure that each group is represented and in a fair way. So you'll find that each group will have to be represented based on how big it is, based on its contribution to the entire population. If a group, let's say, the groupings can be categorized based on the region, it could be gender, anything. Yeah, assuming it's region, and you have people from central, east, west, and north, and you find that north has the highest percentage. Maybe out of 100, north has 40%. Yeah, out of 100 elements, 40% are from north. So it would mean that still north should contribute 40% of the sample size, which I think is fair. It's fair enough. So the other elements we have, all the other techniques you can look at as systematic sampling, whereby you choose elements following a given interval. You take every ith element. For instance, you can take an interval 5 and you select every fifth person. You count 1, 2, 3, 4, 5. You take the element 1, 2, 3, 4. Interesting. Yes, so the trick under this is how you determine the interval. What do you base on to determine the interval you're going to follow? And we do that using a simple formula. You get the population, you divide by the sample size, and then what you get will be our interval. Yeah, assuming I get my population and I divide by the sample size and I get 3, it will mean I will take every third person. Okay, and to make it random, we make sure that the first element or the first person selected is selected randomly. Yeah, the starting point, you arrange your elements in a given order and then you randomly select the starting point to avoid bias. Yeah, because without that you will always be biased. You can be biased. Like if I want a person to be selected, I can tell. I can be like, okay, if I start from here, that person will be the third. So I count in a way that I'll get that person I want. So to avoid all that, you randomly select the first element. And then finally, at times our population, or at times we don't have a sampling frame or a list of elements in the population. So in such situations, we can use cluster sampling, whereby we take an intact group and we study all elements in that group. Okay, so you can then read about the non-probability or the non-random sampling techniques. Yeah, snowballing, one element leads you to the other. You get one thief and that thief leads you to another thief. You get one drunko and a drunko leads you to another drunko, and then that drunko leads you to another drunko, and so on and so forth. So please, you can go on and read about the other non-random sampling techniques. Now let's go to sampling distribution. Let's go to sampling distribution. Yeah, so for any given population of size n, it's possible to get different samples of size n. Yeah, for the population it's the capital N, sample is a small n, and we are saying for every population, if I have my population, let's say made up of 1,000 elements, there's a possibility of having different samples of size n, maybe different samples of 80, etc. Okay, so I think each sample may well have a different mean. So you may find that the different samples from the same population have different means. So you have 3 samples of size, let's say 100. They're all from the same population. So you may find that the first sample may have a mean based on what the catalyst you're looking out, or that bit you're looking out for. Maybe it's age of the elements. You find that the first grouping has a mean of let's say 40 as the average age, and then the other has maybe 30, 20, etc. It's very, very possible that elements from the same population, but rather in different samples, have different means. It's very, very possible, actually. Yeah, it's very, very possible. Okay, so In fact, it's possible to get an entire distribution of different sample means from the various possible samples. Okay. Actually, it's harder for them to produce the same mean. It's more harder than possible to get the same mean. Okay. So if I have like 5 samples from the same population, so if I list all the possible values for statistics, okay, and then the probability associated with each value, then I will come up with what we call a sampling distribution. Yeah, here I'm talking about a statistic. Yeah, but I recall I talked about it earlier in our first lecture. Yeah, just remind you, a statistic, when you talk about a statistic, you're talking about characteristics of a sample. Okay, and then a parameter, we're talking about the population. So a statistic is for a sample, as a parameter is for a population. Okay, yeah, so saying the list of all possible values for a statistic, yeah, and the probability associated with each value is known as a sampling distribution. Okay, assuming I'm looking at age and I'm having 5 samples. Okay, so we are saying that if I list down all the possible values for age and the probability associated with each value, then what I come up with is what we call a sampling. So when the population we are sampling from has or is normally distributed, then chances are that the sampling distribution of the mean will be closer to a normal distribution regardless of the sample size. And here we are having the illustration of that. Yeah, when the sample size is 10, 4, they're all closer, or they're closely normally distributed. Yeah, as the population yeah. So in case the population is normally distributed, chances are that the sampling distribution for a mean in that case will be normally distributed, or approximately normally distributed, regardless of the sample size. And now let's look at this interesting theorem. Yeah, the central limit theorem. Yeah. So this theorem helps us to understand the relationship between. It helps us to understand how the size of the sample um, affects the distribution of the population. Yeah. So in this theorem, it says that for large samples, yeah, those samples which are equal or greater than 30, the sampling distribution of the sample mean can be approximated closely with the normal distribution. Yeah, with that mean equal to the population mean, and the standard error equal to that. So this theorem states that if the sample size is bigger enough, yeah, that is 30 and above, yeah, it's greater or equal to 30, then chances are that the sample mean will be closely associated, or can closely be approximated with a normal distribution. Yeah, and in such situations the mean will be equivalent um, to the population mean, or the sample mean will be equivalent to the population mean, and the standard error will be equal to that. Okay, so this tries to illustrate it. Yeah, so we are having, let me try to show you. Yeah, so we're saying the standard error of the mean is defined as the standard deviation of the sampling distribution of the mean. So here we are seeing the population distribution, and then we are having the mean distribution for small to moderate sample size. This is the mean distribution, and then we have the mean distribution for large n, approximately normal. Yeah, so you're seeing the one for a smaller size is skewed. Yeah, you can see it's a bit skewed, and then the one for a bigger sample size is approximately normal. It's almost normally distributed, like you can see. It's almost bell-shaped. Yeah, it's closer to being bell-shaped, and of course it approximately carries the other characteristics of a normal distribution. I think that's one of the reasons, that's one of the importance of having a larger sample size. Like we said, a larger sample size is closer to a population. Yeah, the findings you get are closer to the findings you would get if you were to use a population. Yeah, we are still continuing the central limit theorem. So based on this theorem, if y bar is the mean of a random sample of size n from a population with a mean mu and a standard deviation that, if n is large, then it has approximated the standard normal distribution, and there we can use the normal conversion formula to get the z. We'll talk more about this z, the z value, yeah, which helps us to measure the area under the normal distribution curve. Yeah, so to get the z value, you get the mean, the sample mean, minus the population mean, okay, divided by our standard deviation over the square root of the sample size, and then we'll be able to get our z values, which we'll look at in more details. Yeah, so this is an example to illustrate the idea of the central limit theorem. So in this example, the population distribution shows 5 levels of a characteristic variable. A characteristic or variable that were measured in the population. Yeah, 5 levels of a characteristic or variable that were measured in the population. Each level of the variable had the same probability of occurring. Recall we say the distribution carries the probability and then the sample means. Yeah, I hope you can recall that. So the population distribution is presented below. Let me repeat the question or the example. In our example, the population distribution shows 5 levels of a variable that were measured in the population, meaning we had 5 samples, okay, with each level having its sample. Yeah, so there's a sample for each of the 5 levels. So each level of the variable had the same probability of occurring. And we are saying the population distribution is presented below. Yeah, so this is the population distribution. The scores in the population range from 1 to 5. The mean of the population is 3, and the standard deviation of the population is 1.41. Let's continue. Yeah, so we are saying the frequency distribution of the sample means quickly approach the shape of a normal distribution. even if we are taking relatively few small samples from a population that is not normally distributed. Yeah, you can see, yeah, this our results down here. Yeah, in this case, our sample size is 25. Here the sample size is 20, and then here it's 100. Here it's 100, and then here infinity. Yeah, of course you can see that for infinity it's normally distributed. For 100 it's closer. Yeah, it's almost normally distributed. And then we have an assignment here. Yeah, we have an assignment here, which you can do with your friends. Okay, which you can do with your friend's guidance. Yeah, and after you will post your answers in our chat room. Okay, I will create a chat room where you will be able to put your answers. Yeah, so please, we can even use that chat room to discuss about where we've not understood. Yeah, yeah, yeah. There could be some areas, maybe even if you replay the video 100 times, you can't understand the concept or that particular concept. You feel free to ask either in the comment section or in our chat room. Yeah. So friends, let's not fear. Yeah, I know I might have been fast in the way that even if you replay and replay, even if you reduce on the speed, you can't get. Yeah, please always feel free to note down. Yeah, and we'll be having live sessions for questions. Yeah, today I've recorded this because of the network issues. I know I may wish to log in for the lecture and it fails. That's why I've decided to record and send you. Yeah, and then you review everything, you do my assignment, and God willing, we can organize, or we'll be organizing some live sessions. Of course, using big blue button. Yeah, to add on what we will have or what I will have recorded. Yeah, so feel free and feel free to ask at any point. Thank you very much for listening. Thank you for listening. Have a blessed day.